You are looking at the night sky, maybe from your backyard, maybe from a dark field far from city lights. And if the conditions are right, you see it, a pale, milky band stretching across the darkness, ancient and impossibly faint. You've known its name since childhood, the Milky Way. But here's a question that will change how you see everything. If a beam of light left from one edge of that galaxy right now, racing at nearly 300,000 kilometers per second, the fastest speed anything can travel in this universe, how long would it take to reach the other side? The answer is 100,000 years, not 100 hours, not 100 days, 100,000 years. And that answer, as staggering as it sounds, is only the beginning of what light's journey can teach us about where we live, what we are, and the terrifying beauty of scale. Before we can understand what 100,000 light years means, we need to understand what light actually is and why its speed matters so much. Light travels at exactly 299,792,458 meters per second. Not approximately, exactly. This number is so fundamental to physics that in 1983, the international scientific community did something remarkable. They stopped measuring the speed of light. Instead, they defined the meter itself in terms of light's speed. 1 meter is now officially the distance light travels in a vacuum in 299,792,450 of a second. Think about that. We don't measure light with meters anymore. We measure meters with light. This peculiar constant was first teased out by a Danish astronomer named Ole Rømer in 1676. He wasn't trying to measure light speed. He was trying to solve a practical problem. How do you keep accurate time when you're sailing across oceans? Galileo had suggested that the eclipses of Jupiter's moons might serve as a kind of cosmic clock visible from anywhere on Earth. So Rømer, working at the Paris Observatory, spent years meticulously recording when Jupiter's innermost moon, Io, disappeared into the giant planet's shadow. But something strange happened. The eclipses didn't keep perfect time. When Earth was moving toward Jupiter in its orbit, the eclipses came a little early. When Earth was moving away, they came late. The difference was about 22 minutes over the course of 6 months. Rømer had a brilliant insight. The eclipses weren't changing. Light was simply taking longer to reach Earth when Earth was farther from Jupiter. By dividing the extra distance Earth travels in its orbit by the time delay, Rømer became the first person in history to calculate the speed of light. His answer was about 220,000 kilometers per second. He was off by roughly 30%, but the principle was sound. Light, which humans had assumed was instantaneous since the time of Aristotle, was actually a traveler with a finite speed. It took another 229 years for Albert Einstein to reveal just how profound that number was. In 1905, Einstein published a paper with an almost mundane title, On the Electrodynamics of Moving Bodies. In it, he proposed something radical. He said the speed of light in a vacuum is the same for all observers, regardless of how fast they're moving or in what direction. If you're standing still and shine a flashlight, the light leaves at 299,792,458 meters per second. If you're traveling at half that speed and shine the same flashlight, the light still leaves at 299,792,458 meters per second. Not faster, not slower, exactly the same. This single postulate shattered our intuitions about space and time. To make the math work, Einstein showed that time itself must slow down for objects moving at high speeds. Space must contract, mass must increase, and nothing with mass can ever reach the speed of light, because doing so would require infinite energy. The speed of light isn't just fast, it's the speed limit of causality itself. It's the rate at which the universe processes information, the thread that stitches cause and effect together across the cosmos. When you look up at the stars, you're not seeing them as they are. You're seeing them as they were, when their light began its journey. And that brings us back to the Milky Way. Our galaxy is a barred spiral, a vast pinwheel of stars, gas, dust, and dark matter rotating slowly around a common center. For most of human history, we had no idea what it was. The Greek philosopher Anaxagoras thought the band of light was caused by the brightness of stars that lay outside the shadow cast by Earth. Democritus suggested it was made of countless distant stars. But no one knew its true size. That changed in 1917, when an American astronomer named Harlow Shapley turned the 60-inch telescope at Mount Wilson Observatory toward a type of star cluster called globular clusters. These are dense balls of ancient stars, hundreds of thousands of them, bound together by gravity, that orbit the outskirts of galaxies. Shapley noticed something curious. The globular clusters weren't distributed evenly across the sky. They were concentrated heavily in one direction, toward the constellation Sagittarius. Shapley's reasoning was elegant. If the Sun were at the center of the galaxy, globular clusters should appear roughly equally distributed in all directions. But they didn't. They clustered toward one side, which meant we weren't at the center at all. We were off to one side, looking toward the galactic core, using a technique involving variable stars called Cepheids, whose brightness pulsates at a rate that reveals their true luminosity. Shapley calculated the distances to dozens of globular clusters. His conclusion was stunning. The galaxy was not 10,000 light-years across, as many astronomers had believed. It was at least 100,000 light-years across, and the Sun lay roughly 30,000 light-years from the center. In one stroke, Shapley had accomplished for our place in the galaxy what Copernicus had accomplished for our place in the solar system. He showed that we were not central, not special, not at the hub of anything. We were residents of an unremarkable arm, 2/3 of the way out from a center we couldn't even see because of all the dust in the way. Modern measurements have refined Shapley's numbers, but not dramatically. The luminous disk of the Milky Way is indeed about 100,000 light-years in diameter, perhaps a bit larger if you count the faint outer regions. It's roughly 1,000 light-years thick in the spiral arms, thicker in the central bulge. If the Milky Way were shrunk to the size of a dinner plate, the disk would be thinner than a sheet of paper. And yet, this paper-thin disk contains somewhere between 100 billion and 400 billion stars. Our Sun is one of them. It sits about 26,000 light-years from the galactic center in a minor spiral feature called the Orion Arm, or sometimes the Orion Spur. From our vantage point, the center of the galaxy lies in the direction of Sagittarius. Hidden behind veils of interstellar dust, that absorb visible light. We can only see it in radio waves and infrared. And what lies at that center? A supermassive black hole named Sagittarius, a star. In May 2022, the Event Horizon Telescope collaboration released the first direct image of it, a glowing donut of superheated gas surrounding a dark central shadow. That shadow is the event horizon, the boundary beyond which nothing, not even light, can escape. Sagittarius, a star, has a mass of about 4.3 million times that of our Sun, crammed into a region smaller than the orbit of Mercury. Stars near it whip around at speeds approaching a few percent of light speed. One star, called S2, completes an orbit in just 16 years, swinging within 11 billion miles of the black hole at its closest approach. Yet despite its mass, Sagittarius A star is tiny compared to the galaxy it anchors. The galaxy is 100,000 light-years wide. The black hole's event horizon is only about 14.6 million miles across. If the Milky Way was scaled to the size of the United States, Sagittarius A star would be smaller than a grain of sand in Kansas. Now, we can begin to understand what it means for light to cross this distance. Light travels at about 9.46 trillion kilometers per year. That number is almost useless to the human imagination. So let's try another approach. Imagine you're standing on Earth, shining a flashlight toward the moon. The light leaves your flashlight and crosses the void. In about 1.3 seconds, it reaches the moon. The moon is roughly 1 light second away. Now point your flashlight at the sun. The light travels for about 8 minutes and 20 seconds before it arrives. The sun is about 8 light minutes away. What about the nearest star beyond our sun? That's Proxima Centauri, a dim red dwarf in the Alpha Centauri system. Light from our flashlight would take 4.24 years to reach it. More than 4 years, traveling at the fastest speed the universe allows. Now, consider Sagittarius A star, the black hole at the center of our galaxy. Light leaving your flashlight right now would take about 26,000 years to reach it. When that light finally arrived at the galactic center, the pyramids of Giza would have been ancient history. The Roman Empire would have risen and fallen. Every civilization you've ever studied would have come and gone. And still, that light would only be a quarter of the way across the galaxy. If light left from one edge of the Milky Way and traveled straight across to the opposite edge, it would take approximately 100,000 years to complete the journey. 100,000 years. Let's put that in human terms. Modern humans, Homo sapiens, emerged in Africa roughly 300,000 years ago. Agriculture was invented about 12,000 years ago. Written history began about 5,000 years ago. The entirety of recorded human civilization, from Sumerian cuneiform tablets to the smartphone in your pocket, fits within 5,000 years. If you multiplied the entire span of recorded human history by 20, you would get the time it takes light to cross the galaxy. If you launched a beam of light from the edge of the Milky Way at the moment the first Sumerian pressed a wedge into wet clay, that light would still have 95,000 years of travel time remaining today. This leads to a strange and disorienting realization. We don't see the galaxy as it is, we see it as it was when astronomers photographed a globular cluster 25,000 light-years away. They're seeing light that left those stars 25,000 years ago. during the last ice age. When they study stars at the far edge of the galaxy, they're looking at light that began its journey before modern humans existed. And if there were astronomers living on a planet near the galactic center, looking back toward us, they would see a planet Earth from 26,000 years ago. No cities, no farms, just a few scattered bands of hunter-gatherers struggling through the ice sheets of the Pleistocene, unaware that they would one day build telescopes and contemplate the light from distant suns. The galaxy is so vast that different parts of it exist in different times, at least as far as any observer is concerned. We are perpetually out of sync with ourselves, our own neighborhood, a jigsaw puzzle of moments separated by millennia. This has practical implications. In May 2022, when the Event Horizon Telescope captured that image of Sagittarius, a star, they weren't photographing what the black hole looks like now. They were photographing what it looked like 26,000 years ago. If the black hole were to suddenly vanish today, ripped from space-time by some unknown mechanism, we wouldn't know about it for another 26,000 years. And here's something even stranger. The Event Horizon Telescope doesn't work like a normal camera. It's a network of radio dishes scattered across the globe, from Antarctica to Spain, from Hawaii to Chile. By combining their signals, astronomers effectively create a telescope the size of Earth. But the data took years to collect and process. The observations of Sagittarius A star were made in April 2017. The image was released in May 2022. That means we were looking at light from 26,000 years ago, captured 5 years ago, processed over several more years, and finally released to a public that could only glimpse it through the delayed lens of scientific verification. The universe teaches patience, whether we want it or not. So light takes 100,000 years to cross the Milky Way. What if we wanted to go faster? What if we sent a spacecraft instead? Consider Voyager 1, humanity's most distant explorer. Launched in 1977, it has been racing away from the Sun for nearly half a century. As of late 2025, Voyager 1 is about 170 astronomical units from the Sun, roughly 25.4 billion kilometers, or about 15.8 billion miles. In November 2026, it will reach the milestone of being 1 light day from Earth, meaning light will take 24 hours to travel from Voyager to us and back. Voyager 1 travels at approximately 17 kilometers per second, or about 61,500 kilometers per hour. That's fast by human standards. It could circumnavigate Earth in about 39 minutes. But compared to light, it's crawling. At its current speed, if Voyager 1 were aimed directly at the center of the galaxy, it would take roughly 450 million years to get there. 450 million years. When Voyager arrived, Earth's continents would have shifted beyond recognition. Complex life might not even exist anymore, and that's just to reach the center. To cross the entire galaxy at Voyager speed would take approximately 1.7 billion years. That's longer than the time that has passed since the first multicellular life appeared on Earth. NASA calculated it this way. Traveling at 17 kilometers per second, Voyager would take over 17,000 years just to travel 1 light year. The galaxy is 100,000 light years across. The arithmetic is humbling. But there's something even more remarkable about these distances. They reveal that our galaxy, unimaginably vast to us, is actually rather average by cosmic standards. The Andromeda Galaxy, our nearest large galactic neighbor, is about 220,000 light-years across, more than twice the diameter of the Milky Way. It contains roughly 1 trillion stars. To our several hundred billion, it lies about 2.5 million light-years away, meaning the light you see from Andromeda left that galaxy before the genus Homo even existed. And Andromeda is coming toward us. The two galaxies are approaching each other at roughly 110 kilometers per second, about 250,000 miles per hour. Astronomers long predicted they would collide in about 4.5 billion years. However, a 2025 study using data from the Hubble and Gaia space telescopes suggested the collision is less certain than we thought. When researchers factored in the gravitational influence of nearby satellite galaxies, like the Large Magellanic Cloud, they found there's roughly a 50-50 chance of a collision within the next 10 billion years. The earlier prediction of near-certain collision in 4.5 billion years may have been overconfident. If the collision does occur, it will be slow and strange. The stars themselves are so widely spaced that almost none will physically collide. Instead, the gravitational dance will distort both spirals, flinging stars into new orbits, triggering bursts of star formation, and eventually merging the two galaxies into a single giant elliptical blob that astronomers have tentatively named Milkomeda. Our Sun, if it still exists by then, might be flung to the outer reaches of this new merged galaxy, or even ejected entirely into intergalactic space. The night sky from Earth, if Earth still exists, would be unrecognizable. Instead of a band of light, the heavens would blaze with a combined luminosity of 2 trillion stars. But we won't see it. Humans won't be around. By the time the collision occurs, the Sun will have already begun its transformation into a red giant, boiling the oceans and making Earth uninhabitable roughly 500 million to 1.5 billion years from now. We are transients, observing a single frame of a movie that runs for billions of years. When you understand the scale of the Milky Way, you begin to grasp something essential about light and time and our strange position in the cosmos. Light is the fastest messenger the universe allows, and yet it is impossibly, achingly slow compared to the distances it must travel. A photon leaving the Sun takes 8 minutes to reach your eye. A photon from the nearest star takes 4 years. A photon from across the galaxy takes 100,000 years. This means we can never know what the universe looks like now. There is no now at cosmic scales. Every direction we look into the past. The farther we look, the deeper into history we peer. The cosmic microwave background, the oldest light we can observe, comes from 13.8 billion years ago, just 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. And even that ancient light, crossing nearly the entire observable universe to reach our telescopes, traveled at the same 299,792,458 meters per second. It didn't get tired. It didn't slow down. It simply took that long because the universe is that large. Here is the humbling truth. The speed of light seems like an unimaginable speed, and it is. Nothing with mass can ever achieve it. It's the asymptotic limit of possibility. And yet, the universe made itself so vast that even this ultimate speed is inadequate. Consider this. The observable universe is about 93 billion light-years in diameter. That's not because the universe is 93 billion years old. It's because the universe has been expanding this whole time, stretching the fabric of space while light was in transit. Distant galaxies, carried by that expansion, are now receding from us faster than light. Not because they're moving through space faster than light, but because the space between us is expanding faster than light can cross it. This isn't a violation of relativity. Relativity says nothing can move through space faster than light. It says nothing about space itself. The universe is under no obligation to be small enough for light to cross. There are galaxies out there whose light will never reach us, no matter how long we wait. They are beyond our cosmological horizon, carried away by the expansion of space faster than their light can compensate. Every year, more galaxies slip beyond that horizon, lost to us forever. The observable universe is shrinking, even as the actual universe grows. And yet, somehow, we are here. We are made of atoms forged in the cores of dead stars, arranged into structures capable of contemplating the distances between living ones. The calcium in your bones came from a supernova. The iron in your blood was fused in a stellar furnace. You are, quite literally, the galaxy become aware of itself. And what does the galaxy see when it looks at itself? It sees that light, the fastest thing there is, takes 100,000 years to cross from one side to the other. It sees that the lifetime of human civilization is a rounding error compared to the travel time of a single photon. It sees that we are small and brief and profoundly unlikely. But it also sees something else. It sees that we looked. We built telescopes and measured parallaxes. We watched moons disappear behind Jupiter and deduced the speed of light. We plotted the orbits of stars around invisible masses and proved the existence of supermassive black holes. We pieced together the history of the universe from the faint glow of microwave radiation left over from its infancy. We did this knowing we would never reach most of what we see. We did this knowing our species might vanish before the light from distant galaxies even arrives. We did this anyway. The Danish astronomer Ole Rømer, in 1676, watching Io slip into Jupiter's shadow, had no idea he was measuring the universal speed limit. He just wanted to keep accurate time. But his curiosity, applied persistently and precisely, cracked open a door that Einstein would walk through 2 centuries later. The astronomer Harlow Shapley, in 1917, measuring the distances to globular clusters, didn't know he was repositioning humanity from the center of the galaxy to its outskirts. He just wanted to understand the shape of the thing he lived inside. That's what the scale of the Milky Way teaches. Curiosity doesn't care about limitations. It doesn't care that the distances are too vast to traverse. It doesn't care that we are small. It looks anyway. It measures anyway. It asks questions too big for any single human lifetime to answer. 100,000 years, that's how long it takes light to cross the Milky Way. And in that number is everything. Our smallness, our isolation, the profound silence of interstellar space, but also our persistence, our ingenuity, our stubborn insistence on understanding a universe that does not owe us comprehensibility. We will probably never leave this galaxy. We may never even leave this arm of it. The distances are simply too great, the speeds too slow, the energies too enormous. Our descendants, if we have any, will likely live and die within a few hundred light years of where you sit now. But we can know the galaxy, even if we cannot cross it. We can map its spiral arms and measure its mass. We can photograph its central black hole and predict its collision with Andromeda. We can trace the orbits of stars that lived and died before our solar system was born. And maybe that's enough. Maybe the measure of a species isn't how far it travels, but how far it looks. Maybe intelligence is less about conquering distance than about comprehending it. Light takes 100,000 years to cross the Milky Way, and in that fact, properly understood, is all the terror and wonder of what it means to be a conscious being in an expanding universe. You are here on a small planet, orbiting an average star, 2/3 of the way out, in an unremarkable spiral arm of a galaxy that contains more stars than there have been seconds in human history. You are seeing the universe as it was, never as it is. You are looking at light that left its source before you were born, before your grandparents were born, before your species existed. And when you look up at the Milky Way tonight, remember, those photons that finally reach your eyes have been traveling since before the pyramids. Some of them have been traveling since before humans learned to speak. They crossed the galaxy just to end their journey in your retina. What you see when you look at the stars is not a picture of the present. It is a message from the past, written in light, sent across distances that make the word far meaningless. And somehow, against all odds, you are here to receive it. The Milky Way is 100,000 light years wide. It took the human species roughly 300,000 years to evolve to the point where we could measure that distance. In another 100,000 years, light that left the far edge of the galaxy today will reach the opposite edge, and by then, our species will either be long gone or something so transformed by time that we wouldn't recognize ourselves. The galaxy doesn't care. It rotates once every 250 million years, and it has done so for more than 50 rotations since it formed. It was here before us. It will be here after us. The stars are born and die, and the galaxy barely notices. But for a moment, on one small planet, orbiting one average star, a species arose that looked up and asked, how far? How long? How big? And then we measured it. That's not nothing. In a universe this vast and this old and this indifferent, a universe where light itself seems slow, where distances defeat comprehension, where the lifespan of a galaxy makes the lifespan of a civilization look like a camera flash. The fact that we ask the question at all is remarkable. We may be small, we may be brief, but we looked. And in that looking, we touched the edge of something infinite. The light keeps traveling, the galaxy keeps turning, and somewhere, right now, a photon that left a dying star at the far edge of the Milky Way is beginning its 100,000-year journey toward a planet that won't exist when it arrives. The universe tells its story one photon at a time. And for now, for this brief moment, we're listening. But let's go deeper, because when you really sit with these numbers, when you let them sink past the surface, they reveal something about light itself that's almost philosophical. A photon, a single particle of light, experiences no time. This is one of the strangest consequences of Einstein's special relativity. As objects approach the speed of light, time dilates, stretching out, slowing down. At exactly the speed of light, time stops entirely. From the photon's own reference frame, it exists in a state of eternal now. A photon that leaves a star at the edge of the Milky Way and travels 100,000 years to reach Earth experiences that journey as instantaneous. For the photon, departure and arrival are the same moment. The entire history of the universe, all 13.8 billion years of it, happens in the blink of a non-existent eye. Only for observers does the journey take time. Only for us, made of sluggish matter, does light seem fast, but not fast enough. The photon doesn't struggle across the galaxy. It doesn't fight the distance. It simply connects 2 points in space-time, and from its perspective, those points are adjacent. The 100,000 light-years between source and destination are, for the photon, zero. This is why physics uses the term light-like for the paths photons travel. These paths have zero space-time interval. They connect events that are, in some deep geometric sense, the same place. We divide things into here and there, now and then. Light doesn't see those distinctions. Light sees a universe where distance and time are just different flavors of the same underlying fabric, woven together so tightly that a journey of 100,000 years and a journey of 0 years are, depending on your perspective, exactly the same thing. There's another way to approach the scale of the Milky Way, one that trades light years for something more visceral. The galaxy is big. We've established that. But how much stuff is in it? Current estimates suggest the Milky Way contains between 100 billion and 400 billion stars. The uncertainty is enormous because we can't count them directly. We estimate based on the galaxy's total luminosity, its mass, the distribution of different types of stars. It's educated guesswork on a cosmic scale. Let's take the middle estimate, about 200 billion stars. Now consider this. If you wanted to count to 200 billion, saying one number per second, without stopping for sleep or food or rest, it would take you roughly 6,340 years. You'd still be counting in the year 8,365 AD, assuming you somehow lived that long. And that's just counting, not visiting, not studying, just saying the numbers out loud. Each of those stars has its own story. Some are newborns, still wrapped in the cocoons of gas and dust from which they formed. Some are ancient red giants, swollen and cooling, nearing the end of their lives. Some are neutron stars, collapsed cores spinning hundreds of times per second, dense enough that a teaspoon of their material would weigh 1 billion tons on Earth. Some of those stars have planets. How many? The Kepler Space Telescope and its successors have revolutionized our understanding. Based on their observations, astronomers estimate there are more planets in the Milky Way than there are stars, possibly far more. Some estimates suggest 100 billion to 400 billion planets, but others go higher. There may be as many as 1 trillion planets in our galaxy, and some of those planets orbit in their star's habitable zone, where liquid water could theoretically exist on the surface. Estimates vary wildly, but a conservative guess puts the number of potentially Earth-like planets in the Milky Way at several billion. Several billion. Each of those worlds, if they exist, is separated from its nearest neighbor by light years. The closest potentially habitable planet we've confirmed, Proxima Centauri b, is 4.24 light-years from Earth. At the speed of our fastest spacecraft, it would take about 73,000 years to get there. At the speed of light, it would take 4.24 years. But we can't travel at the speed of light. We can't even travel at a tenth of it. So those planets remain abstractions. Points of light in a telescope, wobbles in a star's motion, dips in brightness when a shadow crosses a distant sun. We can detect them, but we cannot reach them. We can name them, but we cannot visit. The galaxy is full of worlds, and every single one is inaccessible. This leads to what scientists call the Fermi paradox. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to extraterrestrial life. Fermi did some quick mental arithmetic. The galaxy is billions of years old. There have been hundreds of billions of stars across that time, many with planets. Even if the emergence of intelligent life is rare, even if it's a 1 in a billion shot, the sheer number of opportunities should have produced numerous technological civilizations by now. Some of those civilizations should have developed space travel. Even at relatively slow speeds, a civilization could colonize the entire galaxy in a few million years, a blink of an eye compared to the galaxy's age. So Fermi asked a simple question: where is everybody? That question has haunted astronomers ever since. We have detected no unambiguous signals from alien civilizations. We have found no evidence of megastructures, no signs of interstellar travel, no footprints of galactic colonization. The galaxy is 100,000 light-years across and appears to be empty of technological life beyond our own planet. There are many proposed solutions to the Fermi paradox. Perhaps life is rarer than we think. Perhaps intelligence is rarer still. Perhaps civilizations tend to destroy themselves before they can spread across the stars. Perhaps they're out there but have no interest in us. Perhaps the distances are simply too great, even for civilizations millions of years more advanced than our own. That last possibility is sobering. Even light, the fastest thing in existence, takes 100,000 years to cross the galaxy. What if that timescale is simply incompatible with the persistence of any single civilization? What if the galaxy is full of intelligent species, each isolated by the vastness of space, each rising and falling without ever making contact? In that case, the silence isn't evidence of absence. It's evidence of scale. The universe might be teeming with minds, and we might never know, because the cosmic ocean is too wide and the messages take too long. Let's return to light's journey across the galaxy. But this time, let's watch it happen. Imagine a photon leaving a star at the outer edge of the Milky Way. Let's call this star a red dwarf, one of the most common types, small and cool and long-lived. Our photon is generated in the star's outer atmosphere, an electromagnetic disturbance propagating outward at the universal speed limit. The photon leaves the star and enters interstellar space. Contrary to what you might expect, space isn't empty. The interstellar medium contains about 1 atom per cubic centimeter, mostly hydrogen, a thin fog by any earthly standard, but substantial over cosmic distances. The photon passes through this fog largely unimpeded. Hydrogen is transparent to visible light, and the vast majority of atoms in its path don't interact with it at all. But the galaxy also contains dust, tiny grains of carbon and silicon forged in the death throes of ancient stars scattered throughout the spiral arms. This dust absorbs and scatters light, particularly blue light, which is why distant objects often appear redder than they actually are. Astronomers call this interstellar reddening, and it complicates their observations enormously. Our photon might encounter a dust grain. If it does, that's the end of its journey. The energy gets absorbed and eventually re-radiated as infrared light, a different photon with a different history. But let's say our photon is lucky. It threads through the dust clouds and continues on its way. For the first 10,000 years of its journey, the photon travels through the outer reaches of the galaxy, where stars are sparse and the stellar density is low. This is the galactic halo, populated mainly by ancient globular clusters and high-velocity stars on elliptical orbits. Then the photon enters the disk. Here, the density of matter increases dramatically. Stars are packed more closely, separated by only a few light years on average near the galactic plane. Giant molecular clouds, some hundreds of light years across, loom like continents of cold gas. Some of these clouds are actively forming new stars, their interiors glowing with the infrared signatures of protostars still gathering mass. The photon might pass through one of the spiral arms, structures where star formation is enhanced by density waves rippling through the galactic disk. The Milky Way has 4 major spiral arms: Scutum Centaurus, Perseus, Sagittarius, and Norma, plus smaller spurs like the Orion Arm where our Sun resides. Roughly 40,000 years into its journey, the photon nears the galactic center. Here the stellar density reaches its peak. Millions of stars crowd into the central bulge, a spheroidal region dominated by old, red stars. The gravitational field intensifies. Gas swirls inward, heated to millions of degrees, emitting X-rays that our photon ignores, but our telescopes do not. And at the very center sits Sagittarius A star, the supermassive black hole. Our photon passes within a few light years of it, but isn't captured. The black hole's gravitational influence, enormous though it is, doesn't extend far enough to significantly bend the photon's path at that distance. Past the center now, the photon begins the second half of its journey. Another 50,000 years of travel through the disk, through more spiral arms, more dust clouds, more sparse stellar neighborhoods. Finally, 100,000 years after it began, the photon reaches the opposite edge of the galaxy. It continues into intergalactic space, the vast emptiness between galaxies, where the density of matter drops to almost nothing. If nothing absorbs it, that photon will travel forever. It will cross the void between the Milky Way and Andromeda in about 2.5 million years. It will pass through galaxy cluster after galaxy cluster, superclusters and voids, an endless journey through an expanding universe. And through all of it, the photon experiences no time. For the photon, the entire odyssey is instantaneous. We've talked about distance, we've talked about speed, but what about the structure of the galaxy itself? The architecture that light must navigate. The Milky Way isn't just a flat disk of stars. It has layers, like an onion, each with its own properties. At the center is the bulge, a dense spheroidal concentration of old stars roughly 10,000 light years in diameter. These stars are billions of years old. Population 2 stars with low metallicity, meaning they formed when the universe contained fewer heavy elements. They orbit the galactic center on randomly inclined paths, forming a three-dimensional swarm rather than a flat disk. Surrounding the bulge is the thin disk, where most of the galaxy's stars reside. This disk is only about 1,000 light-years thick, but extends roughly 100,000 light-years in diameter. The thin disk contains younger, more metal-rich stars, including our Sun, as well as most of the galaxy's gas and dust. Star formation is ongoing here, particularly in the spiral arms. Above and below the thin disk is the thick disk, a population of older stars extending to about 3,000 light-years from the galactic plane. These stars are intermediate in age and metallicity, representing an earlier generation of galactic evolution. Enveloping everything is the halo, a sparse spherical distribution of stars and globular clusters extending at least 100,000 light-years from the galactic center, possibly much farther. The halo stars are ancient, some among the oldest in the universe, and they trace the original shape of the galaxy before the disk formed. And then there's the dark matter halo. We can't see it, we can't touch it, and we don't know what it's made of. But it's there. We know because the outer stars of the galaxy orbit faster than they should, based on the visible mass alone. Something invisible is providing extra gravitational pull. Current estimates suggest the dark matter halo extends nearly 2 million light-years from the galactic center, dwarfing the visible galaxy, and contains several times more mass than all the stars, gas, and dust combined. Light traveling across the galaxy passes through all of these regions, influenced by gravity but never captured, bending slightly around massive objects according to Einstein's general relativity. But there's one more aspect of this cosmic journey we haven't explored. What happens when light reaches the very edge of what we can observe? The Milky Way is 100,000 light-years across, but the observable universe is 93 billion light-years across. That's roughly 930,000 times wider than our galaxy. How can the observable universe be 93 billion light-years wide when the universe is only 13.8 billion years old? If light is the fastest thing there is, and it's been traveling since the Big Bang, shouldn't the observable universe be only 13.8 billion light-years in radius? The answer lies in the expansion of space. When astronomers say the universe is expanding, they don't mean that galaxies are flying through space like shrapnel from an explosion. They mean that space itself is stretching. The fabric of the cosmos is growing, and galaxies are carried along with it like dots on the surface of an inflating balloon. In the early universe, this expansion was dramatic. During a period called cosmic inflation, which lasted only a tiny fraction of a second after the Big Bang, the universe grew by a factor of at least 10 to the 26th power. Space expanded so fast that regions that had been in contact with each other were suddenly separated by distances far greater than light could ever cross. This sounds like it violates the speed limit we've been discussing. And in a certain sense, it does. But not in a way that breaks physics. Nothing is actually moving through space faster than light. Instead, the space between things is growing. It's a subtle but crucial distinction. Think of it this way. Imagine two ants on a rubber band, facing each other. If the rubber band is stretched, the ants move apart even if neither ant takes a step. Their separation velocity depends on how fast the rubber is stretching and how far apart they were to begin with. The universe works the same way. distant galaxies aren't racing away from us through space. They're being carried away by the expansion of space itself, and for sufficiently distant galaxies, that expansion rate exceeds the speed of light. This is why the observable universe is larger than 13.8 billion light-years in radius. The light we see today from the most distant visible objects left those objects when they were much closer. As that light traveled toward us, the universe expanded, carrying its source farther away. By the time the light arrives, the source is now much farther than the distance the light actually traveled. The most distant light we can see, the cosmic microwave background, was emitted when the universe was only 380,000 years old. At that time, the matter that emitted that light was only about 42 million light-years away from the matter that would eventually become Earth. But since then, that matter has been carried away by expansion. Today, it's about 46 billion light-years away. The same logic applies to galaxies. The most distant galaxies we've observed are roughly 13 billion light-years away in terms of light travel distance, meaning it took 13 billion years for their light to reach us. But in the time that light was traveling, those galaxies were carried even farther by expansion. Their current distance is closer to 30 billion light-years, and some objects are so distant that their light will never reach us. The expansion of space carries them away faster than their photons can compensate. These objects have crossed the cosmological event horizon. They're still out there, presumably filled with stars and planets, and perhaps even life. But we will never see them, never detect them, never know anything about them. The observable universe is a bubble, and it's shrinking. Every year, more galaxies slip past the horizon. Galaxies that were once visible, at least in principle, become invisible forever. The photons they emit will never catch up. The expansion always wins. In the far future, when the universe is hundreds of billions of years old, observers in what used to be the Milky Way, if any observers exist, will see an almost empty cosmos. All the other galaxies will have disappeared beyond the horizon. Only the merged remnant of the local group will remain visible, a single island galaxy in an apparently infinite void. Those future observers, if they're like us, might conclude that the universe has always been empty. They might have no way of knowing that it was once filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. The evidence will be gone, carried away by expansion, lost beyond the edge of observation. The universe erases its own history. Given enough time, it will forget it was ever full. This brings us to a meditation on cosmic time. The Milky Way is about 13.6 billion years old. It formed not long after the Big Bang, coalescing from hydrogen gas left over from the initial expansion, collapsing under its own gravity, igniting the first stars. Those first stars, called population 3 stars, were different from stars today. They contained no heavy elements, only hydrogen and helium from the Big Bang. Without heavy elements to help radiate heat, they grew enormous, some perhaps hundreds of times the mass of the Sun. They burned hot and fast and died young, exploding as supernovae and seeding the galaxy with the first carbon, oxygen, iron, and all the other elements heavier than helium. Those elements mixed with the remaining hydrogen gas and collapsed again, forming a second generation of stars, slightly richer in heavy elements. Those stars lived and died and enriched the galaxy further. Then a third generation, a fourth, hundreds of cycles of stellar birth and death, each one adding to the cosmic recipe. Our Sun is a relatively recent addition, only about 4.6 billion years old. It formed from gas that had already been through multiple generations of stellar processing. The carbon in your body was forged in stars that died before the Sun was born. The oxygen you're breathing right now passed through at least one supernova. If the galaxy is 13.6 billion years old, and light takes 100,000 years to cross it, then the galaxy's age is about 136,000 times longer than its crossing time. A photon could have crossed the galaxy over 100,000 times since the galaxy formed. And yet, has any photon actually done so? Probably not, for a simple reason. The galaxy has changed dramatically over that time. Stars have formed and died. Supernovae have exploded. The spiral arms have wound and unwound. A photon that set out from one side of the galaxy 13 billion years ago would find a completely different galaxy on the other side if it ever arrived. The thing it left wouldn't be the thing it reached. The Milky Way is not a static object. It's a process, a verb masquerading as a noun. It's a pattern that persists while its components change. Stars are born, stars die, gas flows in and out. The whole structure rotates, warps, collides with satellite galaxies, and slowly evolves. Over the next few billion years, the Milky Way will continue to change. It will exhaust most of its gas for star formation. The rate of new star formation will decline. The galaxy will become redder and older as massive blue stars die and are not replaced. Eventually, all the stars will die. The last red dwarfs, the most parsimonious stars, which hoard their fuel and burn for trillions of years, will finally exhaust their hydrogen. They'll cool and fade, becoming white dwarfs, then brown dwarfs, then cold black dwarfs, emitting no light at all. The galaxy will become dark, not empty, just dark. The black dwarfs will still orbit the galactic center, but no light will travel between them. The concept of how long light takes to cross the galaxy will become meaningless, because there won't be any light to make the crossing. This is the ultimate fate of all galaxies. If current physics is correct, trillions of years from now, the universe will be filled with cold, dark cinders, the remnants of stars that once blazed, and those cinders will continue drifting apart, carried by expansion, until even gravity can no longer hold them together. Physicists call this the heat death of the universe. Not death by fire, but death by entropy, the slow dissipation of all usable energy into cold, diffuse equilibrium. From that perspective, our moment in cosmic history is extraordinary. We exist during the stelliferous era, the age of stars, when galaxies are bright and energy flows and complexity is possible. This era will last a long time by human standards, perhaps another 100 trillion years. But compared to eternity, it's a brief window, a parenthesis of light in an endless darkness. We are living in the universe's fleeting youth. So what do we do with this knowledge? We can despair. The universe is vast and old and will endure long after everything we know is gone. Our lives are cosmically insignificant. Our civilizations are footnotes. Our galaxy itself is just one of hundreds of billions, and even it will fade. Or we can marvel. The same physics that makes the universe so large and so old also made us. The same processes that scattered heavy elements across the galaxy concentrated them here, on this planet, in forms complex enough to wonder about their origins. We are the universe looking at itself. We are atoms arranged in patterns that ask questions about atoms. We are the cosmos made self-aware, at least in this one small corner, for this one brief moment. When you look at the Milky Way and understand that light takes 100,000 years to cross it, you're not just learning an astronomical fact, you're participating in the universe's process of self-understanding. You're a piece of the galaxy, comprehending its own scale. That's not nothing. That may, in fact, be everything. The philosopher Thomas Nagel once asked what it would be like to be a bat. He meant to highlight the limits of our empathy, our inability to truly know what it's like to experience the world through echolocation. But there's a deeper version of that question. What is it like to be the universe? And the answer, at least for now, is it's like being us, being human, sitting on a planet, looking up at the stars, feeling small and curious and alive. That's what it's like to be the universe, in at least one of its many incarnations. The galaxy is 100,000 light-years wide. We are 1.7 meters tall. The ratio is about 5.5 times 10 to the 21st power. We are to the galaxy what a proton is to a grain of sand. Less. And yet, in some meaningful sense, we contain the galaxy. We hold it in our minds. We've measured its diameter, mapped its structure, photographed its central black hole. The galaxy doesn't know itself. We know it for the galaxy. If that's not significance, I don't know what is. What does it mean that we can understand all of this? The Milky Way didn't have to be comprehensible. The universe didn't have to obey mathematical laws. The speed of light didn't have to be constant. These things could have been otherwise, and we would have been left with chaos, patterns too complex to decode. But it turns out the universe is regular. It follows rules. The same physics that governs atoms in a laboratory governs stars in distant galaxies. The same speed of light that Ole Rømer measured by watching Jupiter's moons applies to quasars billions of light-years away. This regularity is the foundation of science, and it remains unexplained. Why should the universe be comprehensible? Why should mathematics, a product of human minds, describe reality so accurately? Einstein himself wondered about this. The eternal mystery of the world, he wrote, is its comprehensibility. When we say light takes 100,000 years to cross the Milky Way, we're making a statement of breathtaking confidence. We're claiming that our understanding of physics, developed over a few centuries on a single planet, applies across scales of space and time that dwarf human experience by factors of billions. And so far, that confidence has been rewarded. Every time we've tested our theories against new observations, from gravitational waves to black hole shadows, they've held up. The universe really does seem to follow the rules we've discovered. That's either a remarkable coincidence or a profound fact about the nature of reality. Either way, it's what makes science possible. It's why we can measure the width of the galaxy from our tiny corner of it. In the end, what does 100,000 light-years mean? It means we are small, but not insignificant. The universe is vast, but it didn't have to produce observers. It didn't have to create beings capable of asking how vast it is. That it did so, even once, even here, suggests something about the possibilities inherent in matter and energy and time. It means we are isolated, but not alone with our questions. Every star you see in the night sky is a sun, probably with planets, possibly with oceans, conceivably with life. The distances are crushing, yes, but the possibilities are not zero. Somewhere out there, statistically speaking, other minds may be looking up at their own night skies and wondering the same things we wonder. It means we are brief, but not invisible. A photon that left a distant star before our species existed will carry information about that star for billions of years. Light preserves the past. The cosmos is a vast archive, and every observation we make is an act of historical recovery. And it means we are bound by physics, but not by ignorance. The speed of light is absolute, but our understanding doesn't have to stop at the horizon. We can deduce, calculate, simulate, and infer. We can build radio telescopes that span continents and space observatories that peer back to the beginning of time. We can measure the galaxy without crossing it. 100,000 years. That's how long light takes to cross our galaxy. And every time you look at the night sky, you're seeing light that made journeys of hundreds or thousands or millions of years to reach you. You're standing at the receiving end of countless cosmic odysseys, each photon carrying information from a distant time and place. The night sky is a time machine. The stars you see aren't where they appear to be. They've moved since their light left them. Some of them aren't there at all anymore, having exploded or collapsed in the years since their light began its journey. What you're seeing is the galaxy's past, 1,000,000 different pasts layered on top of each other like transparencies on a light table. You're seeing 100 years ago and 1,000 years ago and 100,000 years ago, all at once, all woven into a single visual field that your brain interprets as the sky right now. There is no right now at these scales. There's only the past, arriving at different speeds from different distances and converging in your eyes. And the light you emit, the photons that bounce off your skin, the infrared radiation from your body heat, those photons are beginning their own journeys. Some will be absorbed by your surroundings almost instantly. Some will escape into the night. A tiny fraction of them, just a handful, might make it out of the atmosphere and into space. Those few photons will travel outward at the speed of light. In a year, they'll have traveled a light year. In 100 years, 100 light years. In 1,000,000 years, they might reach a distant star. You are, in this sense, broadcasting. Every warm body is. Every light source, every fire and lamp and screen. The Earth is a tiny radio transmitter, blasting signals into the cosmos, most of which no one will ever receive. But the signals go out, the light goes out, and it carries with it the information that we were here. There's a famous photograph called the pale blue dot. It was taken by Voyager 1 on February 14th, 1990, from a distance of about 6 billion kilometers, just beyond the orbit of Neptune. In that photograph, Earth appears as a tiny speck, less than a pixel wide, suspended in a beam of scattered sunlight. The astronomer Carl Sagan, who campaigned for that photograph to be taken, wrote about it with characteristic eloquence. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. Sagan went on to argue that this pale blue dot is the only home we've ever known, and we have a responsibility to cherish it. But consider this. When that photograph was taken, Voyager 1 was about 40 astronomical units from Earth, roughly 6 billion kilometers. Light from Earth took about 5.5 hours to reach the spacecraft. 5.5 hours. That's how long it takes light to travel 6 billion kilometers. The galaxy is 100,000 light years across. That's about 946 trillion kilometers. The distance from Earth to Voyager 1 in 1990 is roughly 158 millionth of the galaxy's diameter. If Voyager 1 made Earth look like a pale blue dot from 6 billion kilometers, what would Earth look like from 100,000 light years? It wouldn't be visible at all. Not just too small to see, but lost entirely in the glare of the sun, which would itself be too faint to detect without highly specialized equipment. From the other side of the Milky Way, our entire solar system would be invisible. That's the scale we're talking about. That's what 100,000 light years means. And yet, we looked anyway. We measured anyway. We asked the question and found the answer and told each other and wrote it down. The Milky Way is 100,000 light years across. We discovered this from a planet so small that it's undetectable from the other side of the galaxy. We figured it out using observations made over a few centuries, a span of time so short that light from the galactic center has barely moved since we started. That's the remarkable thing. Not the size of the universe, not the speed of light. The remarkable thing is that we know. We're dust motes trying to measure the ocean, and we're succeeding. The universe is not beyond our comprehension. It's difficult, yes. It challenges our intuitions. It humbles our self-importance. But it yields to investigation. It answers questions honestly. It doesn't hide. Light takes 100,000 years to cross the Milky Way. We know this because we looked. And as long as we keep looking, as long as there are creatures somewhere in this vast cosmos asking questions about their place in it, the universe will keep answering. The light is patient. The distances are immense. The timescales are staggering. But the questions are worth asking. And the answers, when they come, are worth the wait. The next time you see the Milky Way stretching across the night sky, remember this. You're looking at your home, all of it. Every star you can see is part of this single great structure, this island of light in an ocean of darkness. And light, racing at the fastest speed possible, needs 100,000 years to cross it from edge to edge. You are part of something immense, something ancient, something that was here billions of years before you and will persist billions of years after. And you, for this one brief moment, get to see it. That's not a tragedy. That's a privilege. Look up. The galaxy is waiting. Its light has been traveling towards you for longer than your species has existed. The message is finally arriving. What does it say? It says, you are here. Against all odds, you are here. In a universe of impossible distances and crushing timescales, you emerged. You looked up. You wondered. You asked, and now you know. 100,000 years of light, crossing the galaxy, ending in your eyes. Welcome to the cosmic conversation. You've been expected.